Okay, Arnav, imagine you spent billions of dollars and over 30 years just basically planning and building a machine that just makes two tiny particles crash into each other at nearly the speed of light.
And also hired thousands of scientists. Basically, the world's most expensive car crash simulator.
Pretty much. But instead of airbags, you get Higgs bosons. Welcome to the Large Hadron Collider, or Hadron, however it's called.
Yeah.
I don't know. Sorry.
I think it's Hadron.
Yeah, it is humanity's greatest attempt to play cosmic detective.
Damn, Sherlock Holmes and Sherlock Holmes type.
Yeah.
Let's start at the beginning. Fine.
Yeah, beginning. Back to the beginning.
CERN. CERN is this international lab in Switzerland.
Yeah.
A lot of people would have heard about it. It's like this really big facility.
Yeah.
It basically stands for Conseil Européen pour la Recherche Nucléaire.
Okay.
I mean, I know I dabble somewhat in Spanish. So yeah, I think that's French, but yeah,
Okay.
similar enough. Though that's French for basically we're gonna break particle physics and your budget.
Yeah. So basically, founded in 1954. I think.
Your time.
Shut up. CERN was Europe's way of rebuilding its scientific community after World War II.
Right.
Instead of just all of the countries individually working alone, they pooled their resources together to create one giant research center, which is CERN.
And today it's the largest particle physics lab in the world by far.
Of course.
Thousands of scientists, engineers, and students from more than 100 countries have and continue to collaborate here. The crown jewel. Back to the start of the episode, the Large Hadron Collider. And let's see.
Yeah. Picture this. It's basically like a 27-kilometer underground ring, which is straddling the French-Swiss border.
They're friends, bro. They're best friends.
Yeah.
The
And
border.
it's buried about 100 meters deep, and there's actually a village that is inhabited above that. You can just imagine.
It's safe, right? It's safe.
It's damn safe.
It's safe.
It's a
And inside that large chamber,
chamber,
antechamber,
whatever.
protons, the positively charged bits in atoms, which everyone probably has heard about. I think we've
Yeah.
done so many episodes mentioning them.
Yeah.
They're accelerated to 99.999. No, just 7 nines.
Okay. 7
Percent. The speed of light. It's like sending a Ferrari around the track, except it's doing 11,000 laps every second rather than like one lap every 1.11 minutes, I guess.
Whatever.
1 minute, 11 seconds.
And to basically execute all of this, they use superconducting magnets that are cooled to, I think, minus 271 degrees Celsius, which is basically, for your reference, colder than outer space.
Yeah, so you have conditions on planet Earth that are literally colder than outer space. That's the marvel of
We can
engineering.
create that.
Yeah, very difficult and expensive, but possible.
True.
It's possible. So once those protons are up to speed, those proton beams,
Yeah.
they're steered into collision points. Basically, you taking two Teslas and you're programming them to collide into each.
That's a very extreme example, but
But that's how it works. Like in circles, basically like.
technically, yeah.
Yeah. And when those two Teslas or protons smash and crash into each other, the energy that they create, that's so high, it recreates conditions similar to the Big Bang. Think about that for a second. 13.8 billion years ago, the conditions where the entire universe was
It was just
probably
hot and dense.
hot and dense, the entire universe was condensed into that one ball. Fever.
And
And now we are creating conditions like
yeah, and out of these conditions and the collisions inside those conditions, you don't just get debris like any sort of dust or whatever, but
Mhm.
you sometimes get entirely new particles, and that's really interesting.
And that's where since these particles are so small and they can't be detected by human eyes,
Of
and
course.
And since they have such short half-lives, which are basically their lifespans, you can think about it in the layman's
Yeah.
terms, is basically for us to actually record it and detect it, that's where these large, very sophisticated and precise detectors come in.
That's correct.
So those include giant machines like the Atlas and CMS,
Yeah.
which are basically super cameras. They record the aftermath of the crash in exquisite detail.
Yeah, so the Atlas is basically, like Arnav said, it's one of the two detectors that's there at the LHC. And it has detected like a large range of particles up till now, which also include the Higgs boson. It's also involved in investigating maybe extra dimensions or even dark matter.
I thought you were going to say extraterrestrial, but
no,
that doesn't work.
We actually investigated that in our previous episode.
Episode 4.
If you want to learn about extraterrestrials and if they really are out there, you should check out that.
Fermi paradox.
That's true.
First video episode.
Yeah.
Go ahead.
But coming back to, I spoke about Atlas, now I'm going to talk about CMS. So the CMS is also a detector, and
this full form is compact muon solenoid. Okay?
Yeah, so muons are basically
those
another types of particles within the larger standard model of particle physics that we have.
To give a ballpark amount of like these lifespan things, I think the half-life of a muon is 2.2 microseconds.
Yeah,
we learned that in physics actually. So,
yeah.
So that's how less, like a microsecond is 10 to minus 6 seconds. So these things last very less time.
Yeah.
For like they have a very short lifespan, sadly, compared to humans.
And this compact muon solenoid.
CMS.
This thing is also searching for extra dimensions, and also the broader standard model of particle physics as well,
including particles that could make up dark matter.
Yeah,
that's a ongoing
dark matter and that antimatter
research basically.
Yeah. So it basically has more or less the same goals as the Atlas detector as well. It's just, I would say in very simple terms, a different magnet system design for us.
Basically, it's approaching it from a different point of view for the same goal, to get like two perspectives that hopefully converge into the same answer.
Yeah, like how we not just use one camera but like multiple to gain multiple angles or perspectives. That's exactly what I
use. Yeah.
Yeah, and the most famous discovery of these, of course,
you guys did.
The Higgs boson. That was in 2012.
And that's literally just like 13 years ago. That's so recent that we've confirmed it.
About to be 14. Time travels fast. But what is really time? Maybe we'll find out in the next episode. Keep watching.
So anyways, predicted in the 1960s, but only confirmed by the LHC in 2012. So that's a lot of time to confirm it. That's why it was built. It's part of the Higgs field, as is expected, the thing that gives particles their mass. We've done an entire episode on it. What is the Higgs boson? Yeah, we've mentioned it in at this point so many episodes that I can't really like individually pinpoint, but just for your reference, it's what is mass part 2, and what is the Higgs boson. So if you want to learn more about the Higgs boson or how it gives mass to us, check out those episodes as well. Yeah, because without that Higgs boson or Higgs field, the universe would just be a soup of light speed particles flying around. Yeah. No Higgs is basically equal to no mass, which equals to no atoms, which equals to no us, which equals to no quark. Which is obviously the most important thing, right? Who can live without this wonderful podcast? Exactly, no one can. But beyond the Higgs, the LHC has also been testing the standard model, like apart from the Higgs, because the Higgs is also a part of the standard model. Yeah. And this standard model of particle theory, it's our best theory of particle physics yet. And it's confirmed some of the predictions that we have. Yeah. But it's also left us hanging on more mysteries like supersymmetry or, I don't want to say this, but SUSY. SUSY. Yeah, it's just the short form. Now, in the basically like that standard model, there are a lot of parameters in the standard model equation. Yeah, so there are 19 empirically defined parameters. You might have looked at it on Instagram or elsewhere, but there's like this one whole page that is just one equation. That's a deconstructed standard model equation. And it has, as Arnav said, 19 empirically determined parameters. Basically 19, I would say variables. Inputs, you can say. Yeah, inputs. Like in computer terms. And just to like give like a light overview, it includes 12 fermion masses, 3 coupling constants, 4 parameters for quark mixing, and 2 parameters for the Higgs sector. So yeah, you also know what that means, but yeah, we'll learn that later. And physicists hope that this equation and with its SUSY, supersymmetry, that would help us explain dark matter. But so far, we don't have it. No, nothing, nada. But here's where the LHC matters. It's not about conforming to old theories or confirming also old theories, both ways. Like, it's about chasing the unknown. It's about being curious. Curiosity won't kill the cat, hopefully.
Exactly. And the
There are
big
big
questions
questions. There
are
are big
still on the table. Like, what is dark matter?
Why is there more matter than antimatter right now?
Why is gravity so weak compared to the other forces? And by so weak, I literally said compared to other forces. So you can just imagine the extent to which the other forces are powerful.
Yeah. Another one is, could there be extra dimensions that you already asked earlier? But yeah. And last one is, maybe are we in a simulation? Not officially.
Yeah.
But it's fun to watch.
Of course. And the LHC is also scheduled for a big upgrade that might really help us answer these big questions that are still on the table.
$22 billion big upgrade.
Yeah, and it's called officially the High Luminosity LHC.
Sounds cool.
Of course it is.
It aims to provide more collisions, more data, and thus more chances for weird physics to show up. Maybe more weird. There's quarks literally called strange quarks. So yeah, I don't know what these guys are doing, man. There's so much new strange stuff that can.
Check out our first episode if you want to learn about strange quarks and up quarks and down quarks and all of the different types of quarks.
Sometimes the universe does hide its secrets in rare events like this.
Yeah, and think of this new facility as basically doing something that ups the resolution. Maybe it ups the resolution of the universe's secret.
Kind of like upgrading from Marcus Brownlee SD standard definition to Marcus Brownlee HD, MKB HD, bro, high definition.
Yeah, fun times for them, right? But even if a microscopic black hole actually formed, the Hawking radiation would make it evaporate instantly. So sadly, there would be no apocalypse.
Damn, yeah. But that's up to a certain limit. If it was not microscopic, if it was macroscopic, then yeah, the Earth will be engulfed in a black hole. And the irony is actually, the real irony right now, is that the real danger may not actually be all just these physics experiments. Obviously, there's some of them are dangerous.
Yeah.
But it's more so the public perception about the people misunderstanding these experiments. Right?
But here's the thing. Because of these physics experiments like the LHC, we don't just find particles, but we also create tech.
Yeah, it's kind of like NASA building these new technologies which you've spoken about, like compliant mechanisms, for example.
Yeah.
They created them in advance and now these can be used in real life, real world, normal people applications.
Exactly.
For example, for the Cern, it invented the World Wide Web. Literally, that www, yes, that was invented by Cern, okay, in 1989. Okay?
And what was the purpose?
Just to share physics data. Bro, these guys were levels ahead of everyone that time.
Just to share physics data, okay? Not stupid Instagram reels, meaningless content, TikToks, nothing of that sort. Just physics data. And beyond that, of course, because of CERN, we have advances in medical imaging, superconducting magnets, like for MRI machines, something like that, or even data analysis techniques that literally help how we feed data into AI right now.
The databases for AI.
That AI, artificial intelligence.
Yeah, the buzzword.
Or even something like material science for that matter. Everything's been benefited because of this.
Everything's a food where it's all interconnected, the butterfly effect, as we spoke about in the last episode. Okay, anyways. Plus, on top of all that, it trains, as we said earlier, like generations of scientists and engineers and students that go there to learn and test out their skills. And then they take those skills into other industries everywhere around the world, which again helps everything.